So, because of these light cones being tilted over, black hole can't have a solid surface. In principle, it must be a single point. But it still weighs as much as the whole, whatever it is that formed the black hole did before, probably a big star or something. So you're talking about a very big mass, 10 to the 31 kilograms, say, in zero size.
All right, but there's still, we always talk about the radius or the of a black hole or its event horizon. So that seems to tell you something has a size.
Yeah,
So how do we reconcile
well,
that?
really, the size is zero. I've drawn just a little blue circle there, but of course it'd be far smaller than a pixel. It'd be literally zero size. And this is, you don't normally like having infinities in your equations, but here your density is mass divided by the volume zero, so any mass at all gives you infinite density. And that starts being really nasty, having a sort of infinity in there. But when people talk about the radius of a black hole, they're actually not talking about the radius of the centre. It really is, as far as we know, just a dot, zero size, smaller than the head of a pin. But there is a sort of radius out here which is called the event horizon. This is not the actual radius of anything solid. There's nothing actually physically there. You'd fly straight through it without noticing. What it is the line of no return. This is the line at which those cones are tilted so that they're vertical on the edge. So once you're inside here, you have to move in. You can't stay stationary. Anywhere out, if you try and go away as fast as you can at the speed of light, you could in principle stay where you are or even move out. But once you're inside this radius, all motions take you in.
Okay, so that means what you're saying is that I could, if made out of the right stuff, I could literally travel across that event horizon, and there's not a sign in space that says event horizon or anything. There's nothing there. It's not the surface of the black hole. It really is just the point of no return.
Yeah, so it's
Okay.
maybe a sign, abandon hope, all ye who enter here.
Okay.
But there's nothing going past. You could fly quite happily through here. Just if you wanted to turn around and come back again, that's when you start finding the trouble.
Aha.
And this is also called the Schwarzschild radius, after the theorist who derived it, and it's got this form here, 2gm over the speed of light squared. So you can work it out. It turns out to be pretty small. If the sun was to collapse down to a black hole, we're talking about 8 millimeters for this.
8 millimeters.
Yes.
Like that big.
Yep. So it's, if you've got something that's for the Earth to collapse down. For the sun to collapse down, we're talking about a radius of a few meters. Still pretty small. If you had 100 million solar masses collapse down, you might get about an astronomical unit out, which is still pretty small for the scale of something that weighs that much. So these things are absolutely tiny.
Okay. So imagine then I'm in a spaceship, or let's just say I'm in a circular spaceship, and traveling near the black hole,
Okay,
which
there's one coming in behind you.
is gray in this case, it looks like. So as I come through, I speed up, and just bing, I go away.
Yeah, so from your point of view, you'd just be moving steadily inwards. You'd feel nothing dramatic happen when you cross the event horizon.
Okay,
But from my point of view, as you got closer and closer to the event horizon, the light coming out, let's say you sent a flash every second, the flashes to begin with would arrive every second, but as you came closer and closer, each photon would have to struggle its way out of this intense gravity, so the flashes would come further and further apart. What that means is, from my point of view, you'd appear to slow down. So that last scream as you went across the event horizon would appear indefinitely extended.
And I'd just sort of fade away as I fell into the black hole.
It would also be more and more redshift because the photons have to struggle their way out here, and so the redshift will get greater and greater and greater. So at the moment you're scattering visible light towards me, but that might become infrared and then radio and then 100-kilometre long radio waves or something as that last infrared scream disappears down the event horizon. So for you, you'd be just going pretty fast.
There's one thing I think we should just make sure people understand at this point is that if I'm here, for some reason, find myself at rest outside of a black hole, I will fall into a black hole. But of course, normally one does not find themselves at rest around a planet. In the same way, if we were suddenly to stop here on Earth, the Earth would fall into the sun. It's the fact we're orbiting the sun. So this isn't really a very realistic way of looking at things, is
Yes,
it?
it's a more realistic one that we've given it a bit of a sideways motion. We showed this back in the first course when we talked about quasars. And you see, even a very small sideways motion is enough to stop you falling into the black hole. You just whip around it in an elliptical orbit.
Okay, very good. And so that, in this case, presumably, if I were to go, that elliptical orbit went inside the horizon, that Schwarzschild radius, then I wouldn't come out again.
Indeed. But as long as you stay outside, you actually have to stay outside a bit further outside, because actually when you're really close in, the normal orbital laws don't work because your mass goes up and time slows down. And so actually it turns out there's a radius just outside the Schwarzschild radius where there is no stable orbits. But as long as you stay outside that, and that's very, very small. So if it's an Earth mass black hole, that might be 12 millimeters or something like this.
Okay.
That's a very small target to hit. So by and large, black holes are not very deadly.
And, well, okay, I'm just trying to think what it would be like for me to try to orbit a black hole at 12 millimeters. What would that look like?
Well, if you're going around a black hole, the trouble is not the orbit, you just get round. The trouble is that the orbit's going to be different for different parts of you.
Yeah, because I'm a lot bigger than 12 millimeters.
Yeah, so here's a simulation of a person orbiting a black hole.
Oh, there's very nice likeness of me. Oh, I'm getting, that's not, I really don't want to try to do that.
Oh, I don't know, it's very limber, I'm sure. This is what's technically called spaghettification. You get turned into spaghetti. What's happening is different parts of your body are at different distances from the black hole, and so they orbit at different speeds. So if, for example, your feet were close to the black hole, it would have to orbit faster for centrifugal force to balance gravity. So each time you go around, you get more and more stretched out. This word spaghettification means turn to spaghetti, and it's my 8-year-old son's favourite word.
And so this is sort of the same idea of what we call tidal forces, where parts of your body get pulled on more than other parts of your body, and you tend to get ripped into shreds, or turned into spaghetti in this case.
Yes, that's right. What's killing you is not the gravity, it's the change of gravity across your body. If you're very, very small, so the gravity is not very different in different parts of you, you'll be okay. The larger you are, the more different the gravity will be on one side as opposed to the other, and so the more likely something like this is to happen to you.
Okay.
So
well,
they can be deadly.
So we're not going to be orbiting the Earth as a black hole anytime soon, it looks like.
Well, if you were a good long way out, like 10 metres, you'd be okay. But if you started to get to within millimetres or so, then you'd be in big trouble.
I'm thinking even 10 meters might be a bit ugly.